Well, I want to thank Tawfiq and the other organizers for organizing this meeting and for their wonderful song. So, I'm going to talk about a certain symmetric function and some generalizations of it. This is joint work still in progress with Tewardros Imdeberhan and John Sharashian. So, here is how this symmetric function first arose from work of Imdeberhan, Ono, and Singh in last year. They were interested in this. Well, first, I should say I'm assuming a knowledge of symmetric functions for this talk. They were concerned with the function of a partition lambda of n. Lambda has mi parts equal to I. And phi of lambda is this somewhat daunting looking expression involving Bernoulli numbers, B2K. And what can, well, this number arose as coefficients of certain theta functions expressed in terms of Eisenstein series. So I'm not going to explain that. It's not relevant to the combinatorics. The combinatorial motivation is that they could show that these numbers phi lambda were integers, and the sum of their absolute values was the Euler number E2n. I should say the sign of phi lambda is easy to determine from the known, sign of the Bernoulli numbers. So the sum of their absolute values was E2n, the coefficients of the Taylor series expansion of secant x, and of course, basic fact in enumerative combinatorics that E2n is equal to the number of alternating permutations in the symmetric group S2n, that is, the numbers in the permutation of first increase and decrease, then increase, etc. So this is some kind of refinement of E2n. So what do they count? They should count alternating permutations with some property depending on lambda. Well, this general form of this function, phi lambda in particular, these 1 over mk factorials in the denominator, mk was a multiplicity of the part k, and times some function raised to the mk power, it suggests that these phi lambda should be the coefficients of the power sum symmetric functions p lambda. I'm working in the variables x1, x2, etc., infinitely many variables. So we'll form this symmetric function as a generating function for the absolute value of the phi lambdas. And I'm going to discuss various expansions of AN in terms of standard bases for the symmetric functions. In particular, we want to understand the expansion in terms of the power sums, because that, by definition, is our original problem of understanding phi lambda. It turns out that we can say something interesting about the H lambda expansion. This star just means some coefficient. The expansion in terms of fundamental quasi-symmetric functions, in terms of monomial symmetric functions, in terms of forgotten symmetric functions, and in terms of sure functions, we can say something about all of these expansions. So I'm going to begin with the power sums. First, I want to define the record partition of a permutation. So this is a Gothic A, or Fraktur A to N, the set of all permutations in the symmetric group S2N that are alternating. Now remember, I'm trying to find some interpretation of the absolute value of phi lambda some refinement of alternating permutations, number of alternating permutations, number of elements in A2n. So if we have an alternating permutation in A2n, we'll define W hat just to be the subsequence consisting of the odd indexed terms. So A1, A3 up to A2n minus 1. And for convenience, instead of writing A2i minus 1, I'll just call it BI. BI is the ith term of W hat. Now the record set rec of W hat is a set of indices for which BI is a left to right maximum or record in W. It's like you read W hat from left to right, and every time you see a number that's bigger than all of the previous one, that sets a record. Now the record partition consists of the partition whose parts are the differences between the consecutive records arranged in decreasing order, so that we have a partition. The parts of the record partition are, if the record set is R1, R2 up to RJ in increasing order, the record partition has parts R2 minus R1, R3 minus R2, etc. And then at the end, N plus 1 minus RJ. So in particular, R1 is always 1. Oops, I'll get back to this. Yeah. So R1 in particular will always be a record. So here's an example. Here's a permutation in A10. The odd indexed terms are 7, 5, 8, 10, 9. The records are 7, 8, and 10. They're in positions 1, 3, and 4. So the record set is 1, 3, 4. And the differences between the consecutive terms are 2, 1, and finally 6 minus 4, 2. So the record partition are these numbers in decreasing order 2, 2, 1. And the first theorem is that phi lambda, an absolute value, is just the number of permutations in A2n whose record partition of W hat is lambda. Well, I'll just say a word about the proof. Very quick word. We want to get this expression for phi lambda into a combinatorial form where we can do some combinatorics. And the way to do that is to use this formula for the odd Euler number, E2k minus 1, in terms of the Bernoulli number. You see, it's just this 4k minus 1, B2k over 2k. So we have this nice expression for phi lambda in terms of Euler numbers, and after that we can give a bijective proof of this theorem. Here is an example. For first, here are the expansions of A1 up to A4 in terms of the power sums. Some of the coefficients will be Euler number, A to N, E to N. So here I've done the computation for A2. There's 5 permutations, alternating permutations of length 4. W hat, the 1 and 3rd positions are the 2, 4, 3, 4, 3, 4, 4, 3, and 4, 3. The record partitions are 3 1 1s where the W hat is increasing and 2 2s where it's decreasing. And so we get 3p1 squared plus 2p2. Yeah, kind of interesting how we just look at the odd index terms, look at a statistic on it. Well, to make further progress, it's convenient to make a generating function where these symmetric functions an of x are the coefficients. And the generating function that turns out to work is with this 2n factorial in the denominator. So this will be f of xt. X are the variables of the symmetric function, and t is indeterminate. The index is the nth term. Now we can directly compute just a straightforward computation from this definition of phi lambda. Here's the expression in terms of Euler number, e2k minus 1. It's just immediate from this formula that this generating function is x, the exponential of the sum e2k minus 1 pk t to the k over 2k factorial. If you expand this exponential, like using the exponential formula, you get exactly this product. Now, to go further, I want to evaluate this sum. So we have to look at, forget about the pk for the moment, e2k minus 1 t to the k over 2k factorial. I call this a shifted generating function because the subscript is 2k minus 1, but the exponent is 2k. Well, this is just formally the integral of the usual exponential generating functions for e2k minus 1. If we integrate term by term, we get exactly this. This sum is a tangent, the generating function for the tangent. The coefficients are these odd indexed Euler numbers. And the integral of the tangent is the log secant. So our formula for f of x t, which was this exponential, or you write pk as a sum of xi to the k, and then so interchange the order of summation, so the exponential so we're getting a product over I, since the exp of a sum is a product of the exps of, we're getting a product over I, the sum e2k minus 1, xi to the k, tk over 2k factorial. By my previous slide, this sum is log secant of the square root of xit. It's the square root because the sum originally had a t to the 2k, not t to the k. So of course the exp of a log, that cancels out, and we just get this product, secant square root of xit. So we have this very elegant formula for this generating function, the product over I, secant the square root of xit. Well, as a corollary, we get the theorem that an of x is h positive. If you expand it in terms of the complete symmetric functions h lambda, the coefficients are non-negative. Well, the proof uses it's an analytic proof. It uses the Weierstrass product formula for the cosine. So we have this well-known product formula for cosine. And remember, we're looking at secant of the square root of xit. So secant is 1 over the cosine. That gives us this minus 1. And substituting for t, the square root of xit gives us an xit. So we have this product formula for f of xt, this analytic formula. It's not a formal combinatorial formula. And this product over this term in parentheses, 1 over this fraction inverse, is just this is just a geometric series, we're going to get 4 over pi squared 2k minus 1 squared to the n, and then the product over I is going to produce an hn of x. So here's a formula for f of xt in terms of the complete symmetric functions. Everything is positive. H lambda is a multiplicative function. It's just the product of certain hi's. And so when we expand this out, the product of h lambda will be non-negative. So that's the proof. It's a very non-combinatorial formula for the coefficients of h lambda. It's going to have all these pi's in it for one thing. Horrible sums. Here's what the expansion looks like up to n equals 5. So an open problem is, what are the coefficients? Find a combinatorial interpretation of them. The sum of the coefficients is the Euler number E2n. So we have this other refinement of Euler numbers, but we haven't been able to figure out what that is. The coefficient of Hn here, one can show is n E2n minus 1. This is the number of cyclically alternating permutations in S2n. That is, if we arrange the permutation in a circle, they would continue to alternate all around the circle. But we don't know, well, some of these other h lambdas we can interpret combinatorially, but in general, it's a mystery. Well, it's a surprising connection with a seemingly completely unrelated topic, chromatic symmetric functions. So I'll just briefly remind you of the definition. G is a simple graph, a finite simple graph on the vertex set V1 up to Vp. The chromatic symmetric function of G, you look at all proper colorings of G with the colors taken from the positive integers. So all maps kappa from Vg to the positive integers such that if we have an edge, the color of the endpoints of the edges are different. And then this x of kappa V1, x kappa V2, etc. This symmetric function is telling you how many vertices are there of each color in our color. Not just a number of vertices of n colors, but how many times each color occurs. A simple example is the complement of the complete graph, just p disjoint points. This is saying we can color each point with any color independently, E1 to the p. And for the complete graph Kp, well, all the colors have to be different, so we get an elementary symmetric function. Each choice of p colors is p factorial ways of putting them on the vertices, so we get p factorial EP. If we specialize m of the xi's to be 1 and all the others to be 0, this is the chromatic polynomial of G. Now I have to say something about interval orders. Let's say the script I is a collection of closed intervals, of, let's say, proper intervals in the real numbers. So AI is less than BI. GI is the graph whose vertex set is a set of these intervals, and two intervals are adjacent if let's just say if their intersection is not empty, if they intersect. This is the incomparability graph of the interval order, the partial order that's associated with the intervals by defining AI, BI to be less than AJ, BJ if BI is less than AJ. If the interval on the right is completely, if AJ, BJ lies completely to the right of AI, BI. Now let M be a complete matching on the set 1 up to 2n. In other words, just a partition into n two-element sets. These two-element sets I'll call their elements AI, BI, with AI less than BI. And we'll consider these two element sets AI, BI to be intervals, real intervals. So the set of intervals associated with this matching are these n intervals, AI, BI. And the theorem is the following. If we apply omega, the usual automorphism on symmetric functions, omega to an, omega interchanges the e lambdas with the h lambdas, it's just a sum of certain chromatic symmetric functions, of certain graphs. And those graphs are the graphs corresponding to the matchings on 1 up to 2n. So just think we have an omega of an is a sum of certain chromatic symmetric functions. Here's an example for n equals 2. Well, there's 3 matchings of 1 up to 4. Here they are on the left. Look at the corresponding graph, the incomparability graph of these intervals. Here, the intervals 1, 2, 3, 4 don't intersect, so the graph is just 2 disjoint points. These the two intervals do intersect, so we get these graphs, and their chromatic symmetric functions are E1 squared and 2E2 twice. So omega of A2 is E1 squared plus 4E2. Or, removing the omega, A2 itself is H1 squared plus 4H2. I should say these interval orders IM are not necessarily unit interval orders. So the individual terms in this sum here, the individual terms need not be E positive. The whole sum is E positive because n in general is H positive. So we know that the chromatic symmetric function of incomparability graphs of unit interval orders are E positive, this recent famous result by ICECA, but we cannot use that to show that an is H positive because the sum has non-E positive terms. This suggests two problems just having to do with this set IM of interval orders corresponding to a matching for the matchings of 1 up to 2n. One interesting question, I think, how many of these are actually semi-orders? How many times do we get unit interval orders? For n up to 4, these numbers are 1, 2, 5, and 10. And we can also, how many times does a given interval order occur up to isomorphism in these among these matchings? The number of matchings is the semifactorial function 1 times 3 times 5 up to 2n minus 1. Among them, how many times do we get a unit interval order? For instance, it's easy to see an anti-chain occurs n factorial times. And the second problem is, are there some other nice examples of sums, or maybe even more generally, linear combinations of chromatic symmetric functions being E positive? Of course, ICECA's theorem gives a nice result for a single chromatic symmetric function, and the previous theorem gives a certain sum that's E positive, but whose terms are not. So can that be generalized? Yeah, these are problems that have not been looked at. Okay, now let's take a look at the expansion in terms of monomial symmetric functions. This turns out to be quite straightforward. I'll just illustrate it with an example and make clear the general result. Suppose we look at the A5, the and we want the coefficient of the monomial symmetric function M311. So what we do is we look at permutations of in S10, twice this index 5, and we want the first 6 terms, because 6 is twice 3, to be alternating. Then the next 2 terms, because 2 is twice 1, to be alternating, and then the next 2 terms, again, twice 1, to be alternating. We want the number of such permutations. That is the coefficient of M311. This generalizes in an obvious way to M lambda. So I said the proof is pretty straightforward. Using this product formula for the generating function for AN, there should be a t to the n here. The secant expands. Secant of the square root of xit has this expansion in terms of Euler numbers. So we just write out this product and collect terms, and we'll see that the coefficient of m lambda is just this multinomial coefficient coming from this 2n factorial in the denominator. 2n choose 2 lambda 1, 2 lambda 2, etc. times these Euler numbers, e2 lambda 1, e2 lambda 2, etc. And this is exactly what we count these sequences. We first choose the numbers that appear in the first 6 terms in a multinomial coefficient number of ways. 6 choose 2, 2. 6 choose 10 choose 6, 2, 2. How many ways of choosing the terms in each of these groups? And then the Euler numbers themselves count the number of alternating permutations of each. So a very straightforward proof. Well, I don't have the time to go into details for the expansion in terms of quasi-symmetric functions, but we can easily deduce the expansion of AN in terms of these fundamental quasi-symmetric functions, LS, the Gessel's quasi-symmetric functions indexed by subsets of bracket n minus 1. We can deduce that from the monomial expansion. More interesting are the sure function expansion. We know it's sure positive. This expansion will be sure positive because it's E positive. So here is, again, an example which makes the general case clear. Suppose you want the coefficient of S5311 in the sure function expansion of A10. So take the conjugate partition to 5311. This is 42211. Double each part. We call that partition mu, 84422. And then we'll form a skew-shaped row indexed by 5311. Mu is defined as follows. The lengths of the rows are the part of mu, 84422. And each row begins 1 square to the left of the row above. So this is a skew partition. It's some big shape modulo some staircase. And the theorem is that for any lambda partition of n, the coefficient of S lambda in AN is just the number of standard Young-Caballot of this skew shape. Pretty amazing theorem, in my opinion. And I should mention there's a well-known determinantal formula for the number of standard Young-Caballot of a skew shape, fixed skew shape. So we have a nice determinantal formula for these coefficients. Well, I don't have time to go into the proof, but it's based on the Jacobi-Trudy identity. Okay, that's all I wanted to say about the AN axis. Now I want to talk about generalizations. So I Won't go into the most general possible case. I'll just discuss some that are maybe easier to comprehend from first sight. So the first generalization is to note that the secant of t has this, well-known formula, because inside here we have the cosine of t in parentheses. It's usually the standard expansion of cosine, and secant is 1 over the cosine. Now remember, my generating function for f of xt, the generating function f of xt for these an of x's was this product of secants. So in my first generalization, I replace this 2 by any positive integer d. So I'll call that an d of x. So an2 of x is an of x. And by definition, this generating function is equal to this expansion. It's like a dth multisection of e to the minus x, with this xi to the n, inverse. So I've simply replaced secant with this sum, where we replace 2 by d, and then take the dth root to change this 2n, or this dn, to an n. So that's fd of xt. What about its power sum symmetric function expansion? It's completely analogous to the case d equals 2. Remember, for d equals 2, the coefficient of p lambda was a number of alternating permutations of length 2n, whose record partition of w hat was lambda. For a of nd, you replace alternating permutations with permutations of length dn, whose ascent set is d, 2d up to n minus 1d. When d is 2, this is just saying the permutation is alternating. And we replace w hat with every dth term of w beginning with a1. Exactly the same deal. What about the h expansion of a of nd? For a of n2, remember we deduced h positivity from the Weierstrass product formula for the cosine. Here, this is the analog of the cosine. I'll call it gd of t. Actually, it's the cosine of the dth root, or it's the analog of the cosine of the square root of t. But here we don't have an explicit product formula like we did for cosine. However, these power series, or considered as actual analytic functions, are a special case of so-called Mittag-Leffler functions, and it is known that their zeros are the reciprocal. The zeros are all positive real numbers, and they're distinct, alpha 1, alpha 2, and that the Weierstrass product expansion of g dt is just this simple product. And if you know about Weierstrass products, there's no exponential correction terms or anything to guarantee convergence. In other words, if some of the alpha j's converges. And now, by exactly the same argument as we did for the case d equals 2, you get these AFNDs, or H positive. Now again, I don't know the coefficient. Well, I don't know them for d equals 2, so I'm not going to know them in general. I should say one can actually also prove H positivity of A and D from the d equals, actually, from the d equals 1 case, actually, It's trivial. Using the theory of total positivity, or the main theorem in this subject, the Edray-Thomas theorem. We don't really need this complex analysis, or really the complex analysis is buried in the statement of this Edray-Thomas theorem. Now, the monomial expansion of A of nd is, again, completely analogous to that of A of n2, or A of n. Remember, the coefficient of M311 and A5 we got by doubling these terms of this partition and placing an alternating permutation of length twice the length equal to twice the length of this lambda. And exact analog happens for A of nd, for A of 5, 3, for instance. If you want the coefficient of M 2, 1, I think this is not what I mean. M 5, 3, M 2, 3, I mean. So you want permutations in S, A of 3, 3. So we want coefficients in S9, 3 times 5, because here D equals 3. So we take a permutation in S9 whose ascents occur in the multiples of D positions. So here, just after A3, there has to be an ascent, descents everywhere else. We break it up into these pieces of length 3 times 2 and 3 times 1. And we just want to count the number of such permutations. Completely analogous to the case D equals 2. So here 5 should be 3. There's also a nice Schur function expansion, which is a number of standard Young tableau of a certain skew shape are the coefficients. And I won't give the exact result here, but completely analogous again. Now, my second generalization I'm going to look at is to replace my n factorial with n factorial to the k. So now my generating function, I'll be looking at symmetric functions b of nkx. The generating function is the sum b of nkx t to the n, but now the denominator has n factorial to the k rather than, well, 2n factorial in the original problem. And bnk of x is defined by this product formula. So instead of dn factorial, we have n factorial to the k. We could even more generally look at dn factorial to the k, or even more general things than that, but I'll just stick to this simpler special case. So what is the background for this? That is, what if you forget about this xi to the n, what does this expression in parentheses inverse, what does it count? And this is a theorem due to Carlitz, Scoville, and Vaughan in 1974, and I also found some Q analogs in 1976. Now, Fkn be the number of k tuples of permutations in Sn. So U1 up to Uk are all elements of Sn. The intersection of their descent sets is empty. Then the exponent, well, this k-fold exponential generating function of Fk of n is this expression the reciprocal of the sum of minus 1 to the n, t to the n over n factorial to the k. So one expects intersections of empty descent set intersections to be involved with the combinatorics of this generating of this symmetric function Enk. So what is the power sum symmetric function expansion of Bnk? Well, again, I remind you of the original result. If the denominator is 2n factorial, then the coefficient of p lambda was counting permutations, alternating permutations of length 2n, such that the record partition of w hat is lambda. So for Bnk, it's the same result, except instead of alternating permutations of length 2n, we replace it by k tuples of permutations of length n, whose intersection of their descent sets is empty. And what do we do for the record partition of w hat? We just fix any I between 1 and k and look at the record partition of ui. It doesn't matter what I we pick, because any permutation of these ui's, also has a property that the intersection of the descent sets is empty. So that would be the result for the P expansion. For the H expansion, we have to use some complex analysis, but once again, using the theory of hypergeometric series, we can get that this generating function, minus 1 to the n, t to the n over n factorial to the k, has this nice product expansion. In other words, its complex zeros are real numbers, positive real numbers, each occurring with multiplicity 1, and their sum converges. And really, the sum of their reciprocal converges. Okay. So we get exactly as before. What we need is this kind of expansion with these positive numbers here, H positivity for the BNKs. We don't know what that is, again. And for the Schur function expansion, we're still thinking about that. And my final generalization are going to be Q analogs. I mean, n factorial has a nice Q analog, so we can easily define Q analogs of all of these symmetric functions we've been looking at. Every time we see an R factorial, just replace it by R, Q analog of R factorial. That's Q analog of 1 times Q analog of 2, etc. Where the Q analog of I is 1 plus Q up to Q to the I minus 1. Well, we're still thinking about this, but let me just look at the simplest case, which turns out to be very easy. Namely, in this situation of f d of xt equaling sum of a n d of x t to the n d n factorial, put d equals 1. So originally I looked at d equals 2, and then general d. But the case d equals 1 is really simple, because this is just the exponent inside parentheses. We just get e to the minus xit. So we get f1 of xt is x both minus t, x1 plus x2, etc. So the symmetric function d equals 1, a1 of x is just p1 to the n, or h1 to the n. Right? The coefficient of t to the n over n factorial, or minus 1 to the n, t to the n over n factorial when you expand this exponential. So that's utterly trivial, but the Q analog is more interesting. We'll let a of t now be the sum of minus 1 to the n, t to the n over the Q analog of n factorial inverse. And we're looking at these product I greater than or equal to 1, a of t xi, and call the coefficient of t to the n over q n factorial g n of x. It's going to be some q analog of p1 to the n. And what is it? Turns out to be a well-known symmetric function depending on q. The Schur function expansion, the coefficient of s lambda is the usual q analog of the number of standard Young tableaux of shape lambda. It's the enumeration of standard Young tableau of shape lambda by their major index. It also has this formula in terms of the so-called stable principal specialization of S lambda, and an explicit formula which directly generalizes the Hooke length formula, q to some power, q analog of n factorial, and then q analog of the number, or of the product, well, of q analog of the product of the Hooke lengths at u. Now, since all these symmetric functions we were looking at previously were h positive, we could ask whether gd of x is hq positive. If we expand it in terms of the h's, are the coefficients, the polynomials in q with non-negative coefficients. Well, this is false even for n equals 2. But if we let r equal q minus 1, then we do get what we call HR positivity. Conjecturally. I say a messy combinatorial interpretation of the coefficients is known. Oh yeah, that is true. It's not a conjecture. We do have HR positivity with these symmetric functions g n of x, and we know an interpretation of the coefficients. We're expanding it in terms of powers of q minus 1, not q. Well, much more is known that I haven't been telling you, and even more, I think, needs to be done. So this seems to be a very interesting topic, and I will stop here. So thank you for listening.